All right. Let's see. All right, so this is going to be another exercises stream. So yeah, people have submitted a few. I think Jake in the chat has one that he's talking about in the Discord as well. I got a few from the probability book that we were looking at, but I guess we can start with the log problem. Recording, yeah. Alright, so wait, let me get Discord back open. Alright, so we have a log problem from Jake from Discord. And Jake, how much do you know about logs? So the problem is we want to solve for x, and I'm assuming this is like a natural log, although I don't think it matters. Okay, so log of 4x minus 3 is equal to 1 log minus another, so log 16x minus 12. And then minus log of x. Okay. I'm currently on log, right? Yeah. So do you know any of the properties we might use here? So from what I remember, we have the main thing to remember about log is that it changes multiplication into addition or division into subtraction. So this is a formula that will come up a lot. So it's log of a times b is log of a plus b, or log of a plus log of b. Bad marker. I'll write them over here. So log of a times b, that's log of a plus log b. And then we also have log of a division, a over b, is log of a minus log b. Okay. Hello, singular moduli. Ooh, I like that name. Right, so basically if we have a product inside of a log, it splits as addition, right? This has to do with the properties of the exponential function, right? So here, log of something equals log of something minus something else, right? We can always turn this subtraction into division. So let's do that. Can you use the AC method? What is AC method? I'm not sure what that stands for. AC method. Trying to think if I've heard that. I mean, are you saying A times C like hint that log will be quadratic? Right. I'm not sure what does AC stand for though. I understand the quadratic part, yeah. AC. So yeah, I mean, this is log 4x minus 3 is log 16x minus 12 over x, right? Right. yeah, and then if a log equals a log, then we could just take the exponential to the power of both sides and cancel the logs. So this is, or you can think of it as log is a bijective function, at least from the domain and range where it's defined. And so if log of something equals the log of something else, that's if and only if the inside things are equal, right? And then you multiply by x, and then you get your quadratic. Split the middle term. Well, we don't even have to, because, wait, what do you mean split the middle term? Hello, famished. You multiply the a term to the c in the a term to the c. I mean, I'm not sure what you're saying, but once we have a quadratic, I mean, there's a lot of different ways to solve it. You can just plug it into the quadratic equation, right? So, I mean, I would just multiply. Let's just figure out the quadratic that we have first. So, maybe you're talking about like some way to solve the quadratic, but yeah. Right, and then we can just, move everything to one side. So 4x squared minus 19x plus 12 is 0. Right, and then we're just going to use the quadratic equation. Something wrong with my throat is sore. Hold on. So Rex says an algebraic technique used to factor quadratic. Oh, okay. I see what he's saying. Okay. Yeah. So that's what the AC method is. Algebraic technique used to factor quadratic trinomials of this form, particularly when n is not equal to 1. It involves multiplying a and c, finding two factors of that product that add up to b. Oh, right. You're just talking about factoring. Yeah. Right, yeah. What Rex is saying is just a method of figuring out the linear factors. But that's sort of assuming like that these, that it actually factors into, integer factors. But of course, you can always just plug it into the quadratic equation, and you should get the right answer, even if it doesn't factor, right? Or even if it doesn't factor into like integers or fractions, right? Please don't ask. You will get to the quadratic part by cross multiply. Yeah, I mean, once you have this quadratic equation, then it's just a question of what's your favorite method to solve it. I mean, you could try to factor it using that AC method, I think you're calling it, which is like you want to find. Yeah, I mean, so that's like the way to try to factor this into integer factors. But of course, you can just plug it into the quadratic equation. So I guess if all you want is the answer, I would say the simplest way is probably just to plug it into the quadratic equation. Or of course, you can divide by 4 here, right? And then you just have like x squared minus whatever. So yeah, at this point, I would just say whatever your favorite method is to solve the quadratic. I would just plug it into the quadratic equation, but you can use whatever method you want. Someone called it an illegal move. To do what? Which one? Quadratic equation or the factoring? I wouldn't say either is illegal. It's probably a matter of preference. Plus 48. Did I do something wrong? Can you send a link for a problem? Factoring. Okay, well, if you guys are just asking how I would solve this, I would just plug it into the quadratic equation. So let's just do that. If you want to try to solve it a different way, you can try to factor it. But yeah, I mean, it depends on what you're trying to accomplish, I guess. Um, can't even remember the formula now. So this is 19 plus or minus 19 squared minus 4ac 16 times 12 2a divided by 8. 20 times 20 is 400. Yeah, can't really do it in my head, but I could probably do it in my head. Okay, you're saying, well, also we could just divide by 4 and make all the numbers smaller, so that might that might make things easier. Yeah, I'd probably do that. So this will be divide by 4, so 12 becomes 3. I guess maybe that doesn't really help because you still have the annoying fraction in the middle. 19 over 4 plus or minus square root 19 over 4 squared minus 4ac. Yeah, I guess maybe your method is easier to do in your head, I guess. If you don't have a calculator, but when do you ever not have a calculator? 4ac all over 2a, right? So yeah, I mean I could do it out obviously, but if you have a calculator, it's obviously easier. Multiply these to get 48. What am I multiplying? So what's your question? What's the question? How to figure this out without a calculator? Is that the question? Sure, yeah, we can, like I said, there's like, I mean, we can do this like 6 different ways, right? But I'm trying to figure out what's the problem with what's the problem you're trying to solve. If we're trying to find x, then we can just plug it in the equation, we get it. If you want to try to factor, then yeah, you can factor it, sure. Once you know the factors, then you know the factorization as well, though, so it goes both ways. I mean, they're equivalent. How to get there easier is subjective. If I have a calculator, then this is easier. So that's why I'm asking you. Well, you didn't say that. That has to be a specification in the problem. If you don't say without quadratic formula, then I'm going to use the quadratic formula. It's like pretty obvious, right? I know it can't have negative. Okay. Sure. I mean, this always factors the same way, right? Like you're always going to have the two factors multiplying to be the, the last one. So, I mean, yeah, if I don't have a calculator, I'm probably going to do it that way. But of course, you can, you can also, yeah, yeah. Uh, Right. You know. Not 3, it's 12. Okay, well, Jake, you need to specify these things before you specify the problem. You can't just give me a random log and say solve the problem, and then when I solve the problem, you say no, not that way. You have to specify these things beforehand, right? You need to tell me the actual problem that you're trying to solve. Okay, so yeah, so obviously log can't be negative, so whatever the negatives, if there's a negative solution here, you would throw it out. Whatever the solutions of this that are positive, those are your solutions, and then you're done. So, I mean, yeah, just basically comes down to, can you solve this quadratic equation? I mean, theoretically, you don't even need a calculator. I mean, I can do this math on a piece of paper, so even if I don't have a calculator, this is still the way I would do it. So, I mean, if he's going to give you the problem wrong because you didn't use factorization, all right, well then, yeah, I mean, then you have to know how to factor. Well then, you just need to look up how to do factorization. Yeah, I mean, also you could guess and check too. I mean, this is not that hard to try to guess values. If you know it's an integer and you know it's a small number, you could even just probably guess it. That's another way to do it. 4x squared minus 16x minus 3x minus 12 is 0. X equals... Could I send a complex thing in Discord? Yeah, send it. Put in the Wednesday submissions for problems. Snake King, and we'll take a look at it. Yeah, we'll take a look at a complex number one. Yep. Yeah, like I said, guys, you know, there's a lot of different ways to solve this quadratic. I think the easiest way is to just plug it into the equation, but you can do it the other ways too, but I don't want to go over every single way that you can possibly solve this quadratic equation. There's, you know, at least 3 or 4 different ways. Yeah, you can do the grouping, you can complete the square, you can put it into the formula, but all these ways are equivalent, right? So no matter which way you're solving it, you're getting the same solution, right? Four, 16, no, 4, yeah. So what is this complex? Okay. Right. This one looks cool. All right, so we have another problem from that snake. Okay, so the problem is 1 over 1 plus I to the 14th power. So this is a complex analysis problem. So we have complex numbers, we have powers of complex numbers, and one of the things maybe that's useful to know is that you have this pattern where you take the powers of I, you get I squared is -1, and you multiply by I again, you get -I, it goes back to 1, I, and it just keeps repeating like that. And what we want is the 14th power. Okay. I'm not even sure if this pattern repeating is necessarily going to show up here, but the idea is definitely going to be similar. Jake, I'm unsure what you're still confused about. We had a log equation. We had the solution to the quadratic. We said the positive solution was the answer. All you have to do is plug it into the equation. I need to put it in a geometric form, but I kind of forgot how. So in the geometric form, I think what you're alluding to here is you want to think of this number geometrically. That's what you're saying? So we want some number that multiplies with 1 plus I and gives us 1. So it's like z, or maybe we can think of it as like x plus a plus bi times something, or that is the something, plus 1 plus I. Is equal to 1 plus 0. So you could think of it that way. I'm sure there's probably an easier way to do this, right? But this is one way. So yeah, A plus I times B plus A minus B is equal to 1 plus 0 I. So basically, yeah, A minus B is 1. And B plus A is 0. Or A plus B is 0. I feel like maybe this is one you can just remember, though. Or, yeah, okay, so geometrically, I mean, I guess maybe you want to think of it like this. So 1 plus I is here. It has a 45-degree angle here, and when you multiply by a complex number, you're basically going to get some rotation and then some extension of the radius by the magnitude of the thing you're multiplying by. So we have a 45-degree angle, so the inverse is going to have to be something that's like 45 degrees this way, geometrically, and the size of the vector is going to have to be the inverse of the size of this vector, which is the square root of 2. So this one's going to have radius 1 over the square root of 2. Jake is not confused, is not a root. Okay, guys, we can go back to that log problem if you guys are still confused about it, or if you want to do it a different way. But yeah, so the idea here is that this number 1 plus I on the bottom has basically an angle of 45 degrees it makes from this positive real axis. And so we need some number that's going to multiply with the opposite angle to cancel them out, and the size of the vector is going to have to be the reciprocal of the size of 1 plus I. So essentially it's going to be a number this number on the inside is 1 over square root of 2 times a similar vector, except instead of 1 plus I, it's going to be making an angle that's minus 45, so it'll be 1 minus I. Or actually, I guess, no, that's not right. No, that's probably not right. Hold on. Wait, so... Right. Oops. So we want it to be... One half minus I over 2. Here, I just need to check that this number, we need to find a number that has this property. So this has the right angle because it's making a 45-degree angle in the negative direction here, but I just need to make sure that it has this size, and I think it does. Yeah, because 1/2 squared plus 1/2 squared is 1/4 plus 1/4, which is 1/2, and then the square root is 1 over square root of 2. So basically this number geometrically needs to be the reciprocal of this one, so it needs to have this magnitude and it needs to be pointing in the direction that this guy is. I think it's supposed to be from, okay, okay, yeah. So let's use that de Moivre's formula. So let's rewrite this in polar form. So this is like 1 over e to the pi over 2 would be here, so this is pi over 4. Pi over 4i times square root of 2. That's essentially what I did here, but this would be the polar form of this. Or well, actually, once you do 1 over it, then it would be this. So yeah, this way is probably longer. You could do it this way too, but that's not necessary. So it's 1 over square root of 2. Right. So yeah, what's 1 over square root of 2? I can pull that out to the 14th power. What is that? A equals P E to the RT. Okay, yeah, I'll take a look at yours in a bit, Jake. Right, so yeah, we can pull this 1 over square root of 2 to the 14th power. I'll just pull that out. And then it's 1 over e to the pi over 4i to the 14th power. So I guess we don't really need this, but so what happens here? Every 2 powers basically becomes 1/2. So this is like 1 over 2 to the 7th, I think. Right? And then Matt just do 1 over square root to the 14th. Right, that's what I'm doing here, right? And then, so what is this part? So it's 1 over, well, 1 over this could just be negative, right? So we can just think of this as a negative power. So this is e to the negative pi over 4i to the 14th. And then to the 14th power, you know that when you have an exponent and you do to another power, you're just adding the exponents. So it's this 14 times. So 14 over 4, 7 over 2, yeah. So e to the negative 7 over 2 pi I. And do they want it in rectangular or polar form? Rex, is this what you were saying? Just this? Singular moduli says 1 over 128. What is that a response to? Did I do something wrong? Oh, right. Yeah. You get I. Where do I get I? So this would be the polar form. We could, I guess if you want a positive exponent, you could change this to like, what is it, like, oh wait, yeah, you need to, you could add a bunch of, add a bunch of 2 pi i's, right? Wait, what about this did you not get taught? So, I guess. What am I doing here that's tricky? So we talk 1 plus I, 45 degrees. That's where I get the pi over 4 here. To the 14th power, just multiply. Rex, what do you... I'm confused what you're saying. You get I over 128? I don't think I get I here. Oh, I see what you're saying. Right. Sorry, Rex. Yeah, right. Yeah, so e to the negative 7 pi over 2. So this is just equivalent to negative... it's just positive pi over 2. So that's just I. Yeah, right. Yeah. So 1 over 28 times I. Right. Sorry about that. Right, or I mean, technically the polar form's still correct, right? But I guess it's not like simplified. I guess it depends on what you're saying is the final. Usually you want this to be within like 0 to 2 pi. Yeah. So I guess in the polar form, technically it should be like e to the pi over 2i, but that's just I. I thought that the Moivre's rule was like cosine x. Well, de Moivre's rule just says that the power of a complex number in polar coordinates, the angles just add. So that's the part where we're using the formula is the fact that the angle here is this, negative pi over 4i, and then to the 14th power, the angles, we just take this angle and add it to itself 14 times. So maybe I'm misremembering the exact form of the rule, but I thought the rule was just that if I have a complex number that's like r e to the some angle times I, and I take this to some n power, this is just r to the n e to the n phi I, right? I believe this is the rule, right? And that's essentially what we're doing here. We're taking the radius to the power of the 14th, and then we're adding the angle 14 times. Yeah, but that's equivalent to this, right? Because of Euler's formula. Yeah, the thing you wrote is this, right? Without the r. Cosine is 0, sine is 1. Right. Yeah. Right, Rex is saying that the cosine is 0, that's why you have no real part here. And the sine is 1, and that's why you have the I here. Oh, yeah, you need to know Euler's formula. You have to know Euler's formula. If you know any formula, that's the one you need to know, especially for complex analysis. Yeah, I mean, you almost don't even need this formula. If you know Euler's formula, this is just obvious because you're just using, you're just using your exponential rules, right? You have a power, you have a product, I can split it, it's just r to the n. I have an exponential to an n, I can just put the n in the exponent. So I would suggest this is basically just Euler's formula. Actually, no, this isn't Euler's formula. This is just what you wrote is Euler's formula. This is just using properties of exponential functions. They did not teach me Euler's formula in high school. Oh my god, that's negligence. I heard... Wait, where was that comment? I heard doing banking word problems is easy. Banking word problems? Oh, you mean like money word problems? Okay, so did you was there another, are we okay with this problem? Oh, it says log of 0, which is no solution. Okay, yeah. Sorry, Rex helped you out. I'm sorry I wasn't more helpful on that problem. I have a request using a to the a equals p times e to the rt. So John invests $5,000 in an account paying 11% interest continuously. How long will it take for his investment to turn into $2 million? Okay. I think I'm losing my voice for some reason. I don't know why. Something about my throat feels funny. All right. Yeah, you definitely need to learn Euler's formula. For complex analysis, it makes a lot of the problems easier, especially that one we just did. Okay, so John invests $5,000 in an account. So John goes to the bank, he puts $5,000 in. And this bank is paying 11% interest compounded continuously. How long will it take for his investment to turn into $2 million? Okay, and then Jake said that he's using the formula A equals P e to the RT. I'll put that at the top. Or I'll write it as P of T. Oh wait, yeah, is like P0, the initial principal times e to the RT. And so yeah, this formula, this equation is just telling you you're welcome to our Discord, chat with us, or hire Matt for tutoring. Yeah, definitely. I will be graduating from high school in like 3 months from math and science. I kind of need to lock in. Yeah, definitely ask me for any tutoring help if you need help with that for sure. So yeah, this equation is just saying that you have some initial principal, which is P0. So that would be your initial $5,000 here. And because we have an interest rate that's continuous, we're going to use this e to the RT formula, right? So it's, I guess technically they're not really saying this interest rate needs to be in the units that t is in. So if t is in like years, then this is the 11% like yearly compounded interest. But I'm assuming that's what this is. So this is 5,000 times e to the 0.11 times, what did they say for the problem? Oh, yeah, and then we need to solve for t, right? So we need to solve for which t makes this larger than or equal to 2 million. So when is this equal to 2 million? So now it's just a simple, just have to solve for t. So you're going to divide both sides by 5,000, take the logs, and then, yeah. So divide by 5,000 on both sides. This is like 2,000, 4,000, I think. Yeah. Is that right? No. 400. Can't do mental math in my head today. I don't know, wait, not 400, 800, right? 2, 4, no. Wow, yeah, I really can't do mental math. So 400 is e to the 0.11t. Take the log of both sides. For this. So natural log of 400 is 0.11t. And then, so t is, yeah, I need a calculator for this. But yeah, whatever this number is, that's the first time that we'll reach $2 million. In, I guess, in years, in units of years. If this is a 11% yearly rate. So can anybody plug this in for me? Natural log of 400 divided by 0.11. Hi, Kyler. And why use E again? Can't we just imagine it as a geometric sequence? Oh, not 1 mil, 2 mil. 54.5 years? Okay, I'll just trust you on that. That sort of makes sense to me, because going from $5,000 to $2 million seems like it would take a long time at 11%. So 54 years, that sounds right to me. Yeah, for these problems, it's probably good to check that the answer that you get at the end like makes some sort of logical sense. Like 11% is a sort of normal interest rate. So if you're starting out with $5,000 and you're saying how long will it take to get to 2 million, it should take quite a while. So 5 decades is a while. Yeah, for continuous compounding, it would be nice to, it would be a double infinite geometric sequence. That's a lot of words there, Jeff. I'm willing to believe that, but yeah, I would need to think about that for a little while. Oh, rule of 72. Yeah, that's a good point. Rule of 72 divided by 11, 6.5 years doubling time. Right. And this doubled like 400 is, what is that? 2, 4, 8, 16, 32, 64, 128, 256. That's like 8 doubles, right? So yeah, that sounds about right. 8 times 6.5 is like 52-ish. Yeah, plus a little bit. Yeah, so this looks right. Yeah, according to that rule. Yeah. What was the other question? I think I missed one of the questions. Snake King, you said 2 million is 5,000. Oh. Oh, okay. Yeah. So you're asking me why does it need to be continuous? Okay, so this is a good question. So why do we need to use e to the power of and not like some sort of geometric thing? So continuous compounding means if I zoom in, this is like time t, this is like time t plus epsilon. Basically, so there's 2 ways to think of it. Either I'm going an entire year, I start out with $5,000, and at the end of 1 year, I have now $5,000 times 1.11. So I have 11% more, and it took me 1 year. Or I can break that 1 year into pieces, something like 10 pieces, and I can give out 1/10 of this interest rate every time, but then I'm going to multiply it's going to be compounding. So I start out with 5,000, then I get 5,000 times 1.01. Then at the next step, I get 1.01 of that. So I get another 5,000 times 1.01 squared, and so on. So when it's compounding, I should be making more money because I'm actually making interest on my interest, whereas this one step, I'm only making interest on the original principal. Here I'm making interest here, and then I'm making interest on the interest, and then I'm making interest on that interest that I made on the original interest and the first period and the second period. So E is not geometric, it is analytic. 24-hour stream. No, not today, Jeff. Any other questions about this? So basically, you need the e to the power because e is a limit of this sequence as I'm splitting this domain into more and more pieces and doing the processing the interest compounded so that every little interest you're making in some small period of time is actually compounding. You're making interest on that interest as opposed to just one period of time in which you make the interest. For me, after I solved for t, the answer was 57.4. I forget what I wrote. That sounds close, but a little bit off maybe? Only 6 hours today. No. I'll probably do another 12-hour stream sometime, but not today. Okay, so we all agree on that answer? Or is there a problem? It sounds like you guys are a little bit off. So yeah, I think it was like log 400, natural log 400 over 0.11, I think. Right. Right. Any other questions? All right, so if there's no more questions about this, I picked another problem from the probability book. So this is the textbook that's entitled Grinstead and Snell's Intro to Probability in the resources. And this is on page 354. So this is one of the exercises talking about estimating. So actually, let me give a little background first. So this is page 354. Exercise 1, and we're rolling 24 different dice. And A asks, what's the probability that the sum of the dice is greater than 84? And what we're doing here in these problems is we want to estimate using the normal distribution. Specializes in finance. I'm thinking of going to a college which specializes in finance. Would you recommend it? So would I recommend a college specifically for finance? I think some of the best ones are like NYU. NYU is the only one that I know of off the top of my head. Maybe also like, you know, the big ones like Dartmouth and Harvard probably have good finance as well. But yeah, NYU, Harvard, probably Princeton, you know, any of the UPenns, any of the Ivy Leagues. Get the bonuses before they close shop. Okay, so yeah, who can tell me how we might approach this type of problem? They go over it in this book. Let me write the book here. Just this book is the Grinstead and Snell's Intro to Probability. Page 354, exercise 1. So this section is talking about using normal distributions to estimate distributions where you're taking like the sum of a bunch of independent trials. So that would apply to like rolling a, you know, dice 24 times. Every die is some independent result, and when you add them all up, it should have some mean and standard deviation that like it averages out to. So basically there's some central limit theorem that says this should approach some normal distribution, and this should be about the mean and standard deviation of the whatever the distributions are that you're, you know, adding together. So for instance, if we have 24 dice, the mean here should be about 24 times the mean of rolling a single die. So this should be about the 24 times. What is this number, guys? What's the average number I roll on a die? I think we actually use this for another one. But what's the expected value for a dice roll? The variance is what are you calculating the variance for? Mean is 84. Yeah, we got that. Yeah. Oh, right. Yeah. Yeah. The mean is 84. So, how did you get 84? Mean is 84. So. Yeah, exactly. Yeah, it's a little bit of a tricky question. Yeah. But how did we get 84? So it's 24 dice we're rolling, and the average is what for one die? 3.5, right? Right, so this gives us 84. And why is it 84? Well, rolling one die has an average of 3.5, and when we add random variables, the expected value will add. So we're just rolling 24, it's 3.5 plus 3.5 plus 3.5 plus 3.5, etc. So 24 3.5s is 84. And then what is the standard deviation of the approximating normal distribution if we roll 24 independent die? Well, the variance should add. I think Jeff, you have an answer there for the variance, but how did you get that? 1/6 times 5/6 times 24. I'm not sure about your variance number. How did you get that? Or how did you get the standard deviation? Yeah, I don't think I agree with that. What is p though? We're not trying to hit a single number. This is you're thinking of if we were doing a like a binomial or what a Bernoulli trial. I think is what I'm trying to say. Yeah, I mean, what would p even be? You're saying it's 1/6, but I don't think that makes sense for the problem, right? We don't have like a 1/6 chance of doing what, right? Yeah, it's the probability, but like I don't think that applies to the problem because what would be the success, right? Because we're rolling dice. No matter what the number is, it's not like a success or a failure, right? So this is a little bit different. We need to try to figure out what's the variance. It's not obvious what the variance I think is. It's kind of like a non-trivial computation. So it is a non-trivial computation. I'll save some time here. You would have to add up. So it's basically, where do I have room for this? It's like this. Remember the formula for variance, right? Is it's going to be a sum. That's a terrible sigma. It's going to be every value minus the mean squared, and then I'm going to divide by the number of numbers. So it's going to be 6 because there's 6 possible outcomes. So it's going to be like 1 minus 3.5 squared divided by 6 plus 2 minus 3.5 squared divided by 6, and so on. 1 minus 3.5 squared over 6 plus 2 minus 3.5. Yeah, exactly. Right. Right, that'll be the variance of a single one, and that comes out to 70, I believe. Yeah. So this whole sum, this is the variance, this comes out to 70. Or no, sorry, that's if you multiply by 24. Then it's 70. So that gives us this total standard deviation is going to be the square root of 70. So here's our mean, here is our standard deviation, and the normal curve with this mean and standard deviation should approximate the distribution of rolling 24 dice. Of course, the more dice you roll, the better approximation it is, but I feel silly. This is variance of a uniform distribution. I should know this. Yeah. No, I mean, it's, it happens. Right, so then, yeah, I think, and then Jeff pointed out that it's a little bit of a trick question because we're asking if the sum is greater than this, so we want to use an estimation, so we're going to use a z-value of, we're going to check when the z, well, I guess not a z-value, but when the normal distribution with this mean and this standard deviation is greater than or equal to 84.5. Or I guess I should I'll put z hat here just to be proper. It's not the actual z. I'll call it z hat. And we want to check if z hat what's the probability that z hat is greater than or equal to 84.5, because we're checking if the sum is greater than 84, and because we're only allowing discrete values, we have to, this is like a continuity correction, essentially. What is variance? Great question. So the definition of variance is kind of like right here. We're going to take all the values that the function or the random variable can take. We're going to subtract the mean and then square it and then add them all up and divide by the number of elements. And the variance just is a notion of like how wide the distribution is. It tells you, yeah, I mean, it's literally like the visual is like how wide this bump is. You could squish it together, that would mean the variance would be smaller, and if you flatten it and spread it out, then that means the variance is larger. So the variance just tells you how much the distribution varies. What Jeff said, 0.5 divided by square root of 70. Oh, right. Yeah, 0.5 divided by square root of 70. Exactly, yeah. Yep. Yeah, so we have some value like right here. And we want to know what's the area under this curve. Okay. So yeah, all we want to do is we want to normalize to get to the standard normal variable here. So that will be what Jeff is doing there. Yeah, using the error function, you want to use a z value of, so you use 84.5 minus the mean, which is 84. So you're going to get an actual z-score of 0.5 divided by the standard deviation, square root of 70. And then you're going to go to your calculator or to Wolfram Alpha or whatever integral calculating algebraic system you have, and you're going to plug in this z value, which is approximately like 0.04769, I guess. And you're going to plug that in. Or no, sorry. That's not the z. I'm looking at the wrong one. Right, the z value is like 0.0598, I think. That's this. And then if you figure out what's the area greater than here, you can type in like normal CDF. You type in this number, it'll give you this area. And then you can do 1 minus that. So I believe this is like something like a little bit more than 50%, so this is a little bit smaller than 50%. And the shaded in area is equal to about 47%, 48%, so 0.4762. And that should be your final answer for part A. So the probability that the sum is greater than 84 should be approximately, remember this is an approximation because we're using the normal distribution with this mean and this standard deviation just to estimate this because it actually is a discrete distribution. But if we use this estimation technique, then we get about 47.62% chance that it's the sum of the 24 dice is bigger than 84. Or you can use a table. Yeah. If you have a table in a book, you can use the error function table. That will just give you the area under the normal curve for the standard normal from some z value. So you just calculate the z value, you look it up in the table, and you might need to do like a 1 minus thing because the table usually just gives you the areas that are to the left of the value. To find the area to the right of the value, you just do 1 minus that. And then you get this. And you should check, I think Jeff said it before, that the area should be under 50% because the sum is greater than 84 and not greater than or equal to, so we need to start a little bit above the mean, so this should be a little bit less than 50%, and it is. So I think that makes sense. Does this look correct to you, Jeff? Oh, hey, Zach. You said the normal approximation gives us a value for p of sum less than or equal to 23. Yeah. Right, if you look it up in the table, yeah, you'll get p less than or equal to 23, and then you'll just do 1 minus that, and then you get this one. Or wait, 23 or you mean 83, right? Not 23. It's probably a typo, I think. Yes it does, but that's no guarantee it's accurate. Oh, the table or? The table should be pretty accurate if you have the z value accurate. It's pointing out the normal distribution has issues. So there's one more part, which is part B. And part B is the same question, but what's the probability that the sum is exactly equal to 84? And we want to estimate it again. So same type of question. I'll leave the mean and the standard deviation up here. This is part B. So we want to know what's the probability that the sum is exactly 84? And so how would I tackle this problem? Because it's a little weird when we're asking the question, what's the chance that the probability is exactly equal to 84? Because the chance that we pick a value that's exactly 84 in the continuous distribution is actually just 0. So we need to do some sort of like trick here, which we kind of just did for part A as well. But so what types of values should I be looking at in the normal distribution to estimate this probability of the sum being exactly this value? You can actually get it without a table. Means half the width of 84 is that and double it. Yeah, once you have one, you can get the other one. Is that what you're saying? Or are you saying something else? Yeah, so I had to think about this one for a little bit. I had to think if this made sense, but I think we can just check if, the continuous version of the normal distribution with this mean and this standard deviation, if this is between like 84.5 and 83.5. I think that makes sense, right? Oh, are you talking about part B or part A, Jeff? Oh, you're saying you can get part B from part A? Oh, I think I see what you're saying. Right. Yeah, Snake, if you're lost, just ask questions. What are you lost about? Yeah, I agree, Jeff. Yeah, you can get part B from part A, right? Yeah. Because we know this area, we're trying to figure out this area in the middle here, and we know this area is the same as the other one. So we can just do 1 minus 2 times this. So it should be 1 minus 2 times our answer from part A. So this is approximately, so it's 1 minus 2 times 47-ish%. And so this leaves us with 4.769%. So that's saying that if we roll the dice 24 times, the chance that we actually get the mean, the most likely value, is only less than 5%. So we're still most likely just going to get some value that's like close to 84, but not exactly equal to 84. Like sometimes we're going to hit 81, 82, 83. Sometimes we'll hit 85, 86, 87, 88, 89. Only less than 5% of the time will we actually hit this exact value, approximately. But remember, we're estimating here. Yeah, it seems a little bit high to me, as well. Is it correct though? I think it's just that every other value is very low. So like, this is like 4%. You know, all these values out here are just really tiny, so they don't really contribute anything. Remember the variance is the standard deviation is approximately 8.3. So you're really only getting values that are really close to 84 within like 16 numbers. So you're getting a lot of things that are within like 100 to like 58 or something. That's most of the numbers. Yeah. And everything away from 84 is even smaller than this, right? So yeah, they're not equalish. Yeah, this is the highest number, and then they drop off exponentially fast, right? So only the numbers that are really close to 84 are anywhere near this, and the other ones are exponentially decaying towards 0. Okay. Yeah, Snake King. Don't worry about it too much. Oh, my math knowledge is so far behind. Because the probability problems I were used to so far were like 6 tickets to a concert are randomly distributed among 10 interested people. Among them, there's one couple and one group of 3 friends. Both groups would like to attend the concert together. Determine the probability that at least one of the groups. Yeah, we can do problems like that as well. I just happen to not pick them. I mean, this is just a different type of problem where you're trying to estimate using the normal distribution. We can do more probability problems though. If you have a problem for next week, definitely put it in the Discord. And yeah, again, if anybody wants to donate to the stream, keep the stream going so I can keep doing this, that's the link right here is the Ko-Fi link, or you can email me and talk to me about supporting the stream some other way as well. Of course, ask for tutoring if you need any tutoring help. And we'll sign off in a second, but Jeff says my joke was that P of x less than or equal to 23 has a non-zero estimate but a 0 probability. Has a non-zero estimate but a 0 probability. Why? Oh, I see what you're saying. Right. Well, that's always the problem with the using the normal distribution for discrete values, right? For a discrete value, it's obviously the range of possibilities is always finite, right? But the range of possibilities for the normal distribution is always infinite. So that's you're never going to avoid that when you're doing these types of estimates. Yeah, I think that's all I got for problems for today. We'll do more next week. We'll do more probability problems, and Friday I'm going to continue going over the random processes that we've been doing in the Shreve book. So it's, I think his name's Stephen Shreve. Maybe I'm getting that wrong, but it's Shreve. The book is called Binomial Asset Pricing Model, and yeah, we did kind of like the first couple pages last time. We'll go into the multi-period model next time, where the stock is allowed to go up or down, and it can change through multiple different periods of time. Okay, let's try to raid someone. Who is good to raid here? Yeah, if you stick around the channel, you'll pick it up eventually. Obviously, I can't teach to the same level of everyone. Everyone's going to be at slightly different levels, but I'm trying to make the material accessible to as many people, but as well as being accessible to everybody, as also being not overly simple, so that people that maybe are interested in a little bit more higher level math can still follow along and maybe develop higher intuitions for some of this stuff. But yeah, let's see who's streaming right now. Who can I raid? Let me see. Obi is on. Okay, perfect. Raid and Simplex Pachinko. I think I spelled this right. So let's all say hi to Obi. And I hope everybody has a good day.